Okay, everybody close your Chromebooks. Whether you want to or not, you should probably take out a piece of paper to take a couple notes. Because when I get done lecturing, I'm going to try the lecture thing today. Hey, listen, close your Chromebooks, get out a piece of paper, take some notes. So I'm going to try the lecture thing today, and we'll see how we get through this. What I've done to try to get people to actually watch online and actually pay attention in class is I made a little Google assignment that just has a couple questions. It's like, I think 4 questions. It's going to have some very simple questions. They're going to be multiple choice. And at the end, there will also be a little code that you have to put in that I just kind of made up just so it's just another thing to hopefully get people to watch the video. Because I guess you could probably look up all the other answers.
Say the code in the video?
Yes, yeah. I'll probably show it to him. But so just a real quick rundown of what we're doing this week. We will have a couple assignments this week. I guess today's just going to be lecture. So there is the Google Classroom assignment, but it's not an actual Discovery Education assignment. But to be fair, I'll give you all a grade for it, like a daily grade. So we'll probably have 3 assignments today, this week. Tomorrow we'll do an assignment on what we're lecturing on today, and then we'll probably have another assignment. I guess one of them will be a constructed response. The other one will be a multiple choice one. And then Thursday we'll probably study for the 6 weeks test, and then Friday we will have the 6 weeks test. If you weren't aware, this is the 6 weeks, the 6th week of the 6 weeks. And so you should probably have tests in all of your classes this week, unless you've already taken them. But time's kind of going by very quickly, at least for me. I don't know about y'all. Congratulations to the homecoming football win. Pretty nice. I was happy to see that both y'all won and the Stars won. So yeah, I'm not gonna lie about that. I did get most of your grades in that you've done so far. I still do have a couple constructed response things that I have to go through and grade in Discovery Education, but all the multiple choice grades are in. I think there's only maybe 2 or 3 that I still haven't put in. Also, your test grades are in. So if you want to look at the test, I think there was a 5-point curve for everybody. So there you go. So let's go ahead and get started. I'm going to try to get through this pretty quickly, so everybody kind of gets a chance to do the assignment at the end, although it shouldn't take you very long. Real quick. Sorry. My nose is a little runny.
Your mask is down, Mr. Bad.
I know, just for a second.
All right.
All right. I ordered some more of these masks yesterday off of Etsy. They're pretty good. I like them. I like the way it ties and it doesn't go over your ears. Okay, so I am recording, right? Yes, nice. So we are in Stars and Galaxies today. This is the first page. I have assigned this. So if you need to go back and reference anything that you see here, you just click on the reading assignment and it'll be in. I've also assigned a couple of the videos. You do not have to go in and watch them yourself. We're going to watch the important parts of them today. But they are there if you do happen to want to go back and watch them, or if you missed something, or for the people at home, if you can't really see the video through my little video, which I don't know if you will or not, we'll have to see. But yeah, what we're talking about today is stars and galaxies. So page 1 is going to be about stars. Page 2 is going to be about galaxies and the types of galaxies, which shouldn't be too difficult. What they're talking about here is really more the life cycle of stars and what they do, how they do things for us. And so one thing to know about stars, they go through predictable changes over time. You'll see that I have some of this already highlighted, so I'm going to kind of try to stick to the important points and not just read the entire thing. Obviously, stars are very, very hot. And one of the things we talked about when we were talking about the galaxy, our galaxy as a whole, not necessarily galaxies as individuals. No, sorry, I'm using the wrong term here. Our universe as a whole was that when the Big Bang happened, there's really only hydrogen and helium. So at some point in time, we had to create these other elements. We had to create iron and nickel and oxygen and silicon and all the different elements that we have today. And so those elements are made in stars. And so essentially, let's go ahead and watch this first part of this first video because this will describe it a little bit better. I skipped over some of it. Basically, what they're going to talk about here is if you took this soccer stadium, you can tell the guy's British, so they're going to talk about soccer and not football. If you took this soccer stadium they call it football, but we call it soccer because we already have a football. To be fair, you can make fun of the name. Their football is a better name for football than our football because you rarely kick the ball with your foot. In fact, most of the players, you can't kick the ball with your foot. So maybe we should call it something else. And the name football was already taken. But
you can't call it handball.
The handball, yeah, but you could call it like literally anything else that you wanted. I don't know what you should call it, but there was already a sport called football when we made our football. So just saying, I'm just saying. They fill this football stadium with helium and hydrogen, and then they talk about compressing it down. And so they're going to compress it down to like the size of a soccer ball. Actually, hold on. I have my speaker back there. Let's bring it up here.
The atoms of gas start bouncing off each other.
Sorry, that's
and the temperature begins to rise.
So your temperature begins to rise.
By the time it's compressed down to the size of a soccer ball, the hydrogen reaches the critical 10 million degrees, and a process called nuclear fusion begins.
We also call it nucleosynthesis.
The hydrogen starts to fuse together, making a new, heavier material, helium. With every step of this tiny bump and grind, some matter gets converted into pure energy. We have created a miniature star.
Did we really do that?
We're working on it. But not yet,
Of course, if this was a real experiment, you wouldn't want to go anywhere near it.
Like that would go like that.
The energy given off even from a star this small would be devastating.
So, where did you make it at?
Okay, I didn't need all this destruction thing. So they are working on this. This would be called sustained nuclear fusion. It would basically produce enough energy, electricity, to power the entire world pretty easily. Where you'd have to make it in is a very safe lab, and the way you keep it contained is through powerful magnetic fields. We don't have the ability to do this yet, but they're getting closer and closer and closer. Every time you read an article about it, they say we're about 20 years away. So 20 years from now, we'll still be 20 years away because I guess they don't have good self-awareness. But basically what he described is when you compress, you get enough gravity and enough pressure pushing down on all this hydrogen. Eventually, the nuclei will fuse together. And so you get two nuclei from hydrogen fused together and you make a helium. That's called nuclear fusion, or in Discovery Education, they call it nucleosynthesis. And so that is how we create bigger and bigger elements. So if we come back here, they actually talk about nucleosynthesis maybe a little bit further down. Yeah, they talk about nucleosynthesis right here. And it's basically the process of making bigger and bigger elements because it doesn't stop at helium. If you push a hydrogen and a helium together, you get lithium. If you push lithium and another hydrogen together, you get the next element up. And it just gets bigger and bigger and bigger until you have more and more different types of elements in your star. Which, by the way, these elements aren't going to burn the same way that hydrogen burns. And so at a certain point, when you convert all of your hydrogen or a certain amount of your hydrogen into these larger elements, your star stops burning and it starts to enter into the last part of its life cycle.
How do you compress them together?
Gravity. you have that much. I mean, if you're thinking about inside of a star, you have an immense amount of mass.
So how would we compress them together?
Oh, we have to use magnetic fields and super high pressures. I don't really know the details of it. That's like college level physics experiment stuff. But you could probably read a pretty good paper or watch a TED talk on it. I bet there's some pretty good ones. But yeah, you'd have to make an immense amount of pressure. So when you look at the machines, they're these huge machines that take up rooms like bigger than this. And it's all magnets and metal and pipes, and you don't get to see really what's going on inside. And we've done it for small portions of time, but not sustained, and it doesn't put out more energy than we have to put into it right now. The whole point of doing this is if you got to get something out of it.
Right.
So if it costs us more energy than we get out of it, it's not worth it. And so it's just a science experiment now. It's not a practical thing to do. But they are slowly solving little problem after little problem, and they think that one day they'll be able to actually do it. So a couple things about stars. Once your nuclear fusion begins, it's essentially like an explosion. In order to have a stable star, that outward pressure from your explosion has to be balanced by the inward pressure of gravity. And so unless you have enough gravity, first off, if you don't have enough gravity, you're not going to get that fusion in the first place because there's not enough pressure. But you kind of have to have a balance between that outward pressure from that explosion of the fusion and the inward gravity pulling it in, and then you can get a stable star. So they talk about the stable period of a star's life cycle. The more material a star has, the faster it's going to burn through it. The bigger stars live shorter lives because they burn through their fuel much, much faster. In the same way that a large pickup truck has a huge gas tank, but will have to fill up at the gas station more often than a little tiny car that has a smaller gas tank. It does have more gas, but it also burns through it much, much faster than the smaller cars do. And so big stars live shorter lives. Really small stars, although they have less gas to burn, they live much longer lives because they're much, much more fuel efficient, for lack of a better term. Also, the stars that are bigger burn hotter. In general, there are exceptions to that. But no, hopefully you know the hottest part of the flame is blue, and the cooler part of the flame is like red, with yellow kind of being in the middle. So your blue stars are going to be the hottest stars. Your red stars are going to be the coolest ones.
So our sun's not very hot.
Our sun is pretty average. As far as we see throughout our galaxy and the universe, we have a pretty average star, which is nice because if it's too big, we have gravity issues and our planet would be unstable. If it's too hot, we'd have to be really far away from it to not burn up. We have a pretty nice medium, like Goldilocks kind of star.
So like red giants will be the cooler stars?
Yes, they're bigger, and those are actually towards the end of a life cycle of a star, which we might go over in a little bit.
What about white? Is white one too?
White is going to be a little bit different. We will actually see a chart in a second, and I'll kind of go over the colors and some of the temperatures. I think some of the white ones are actually pretty hot. Yeah. Yeah. And we'll have a nice chart in a second called the Hertzsprung-Russell diagram. So hotter stars appear bluer, cooler stars appear more red. They talk about apparent magnitude and absolute magnitude. Apparent magnitude is how it looks from here on Earth. That's just when we look out there, what is the brightness? How bright is it? That's magnitude. If it's from Earth, it's apparent. This is how we see it. It's apparent that it's bright. It's apparent that it's dim. Absolute magnitude, we kind of even everything out. And we basically say, I think it's like 32 point something light years. If we were 32 point something light years away from it, how bright would it be? And we even everything out so we can know, is this star actually bright, or does it just look bright because it's close to us? Or does it just look dim because it's really far away from us? If we were the same distance away, how bright would it be? The same way that, Damien in the back might not think that I'm super loud, but Johnny up here in the front is like, he's always just screaming right in my ear. because I have a very loud voice. But you're further away from me, so you're not getting all that volume. He's closer. But if we evened you out and sat you on the same row, you'd both hear me in the same kind of distance. So apparent magnitude is somebody's closer, somebody's further away. Absolute magnitude is everybody's at the same equal distance, so we really know how bright it is. So we come down here, and they're going to talk about nucleosynthesis. And basically, like I said, the idea is at a certain point, you've combined all your hydrogen into bigger and bigger elements, and the stars just keeps combining them, and it really can't produce anything heavier than iron. And so once a core is mostly iron, not all the way, but once it gets to a certain percentage where the core of the star is iron, your fusion slows down a lot and almost stops. That's when your star starts to die, and it enters into the final stage of its life. For a lot of stars, that's going to be that red giant phase. Your star actually expands, and that's one of the things I talked about earlier, why the Earth has like a limited time frame, because eventually our star is going to run out of fuel. It's going to turn into a red giant. It will expand outward, and the diameter of the star will go past where the Earth is right now. And so it's going to be billions and billions of years from now. But at some point in time, the Earth will, as a planet, will be destroyed. Whether we're here or not at that point in time, we don't know. But the Earth has a limited time frame that we can actually be on it.
What do you think, like the center of the star, what it looks like? Like it's core. Do you think it's like liquid? Do you think it's like smooth?
Well, when you get to that point, it's going to be difficult to describe because there's so much stuff going on. Because it's hot enough, absolutely, to be liquid, but the pressure probably causes it to be something other than a liquid, maybe a solid. And when you get into things that are that extreme, when they get into physics, they get into crazy superposition states, which don't really necessarily fit into those categories of liquid and solid. One day we might be able to figure that out. Here in the Earth, like we know that our inner core is a solid. It's way hot enough to be a liquid, but the pressure from just the Earth itself makes it a solid. It acts as if it's a solid. The outer core is liquid, and the mantle is like it is a liquid, but it's closer to a solid because the temperature is kind of lower.
So this is like a stupid question. Let's say
No stupid questions.
Let's say we got all the water in the universe, right?
Yeah.
And all the ice and stuff. Do you think we could put out the sun?
Probably not. In the universe, I don't know how much water's in the universe. You couldn't take all the water in our solar system and put out the sun. It's too big, too much energy. And so maybe if you got all the material from the universe and put it towards just one of the stars, you might be able to affect it. But really what's going to happen, the temperature is so high, before it even gets to the surface, it's going to evaporate and kind of blow off into space. And so, I don't know that that's practical. But that's the kind of thinking that astrophysicists think about. Like, it's just what if question. What would happen if we did this? What would happen if we did that? That's what you have to get to when you get to star kind of stuff, because we can't actually do any of this stuff. So it's all what ifs, and it makes you think about different things that's going on with the stars. So hold on. It's inside something, so I don't know about like textures. What we found out, the more we look at the star, it's much more dynamic, and there's more stuff going on than we thought at first. We thought it was just kind of a glowing ball, but there's lots of different features and different things going on. So one of the things they talk about, I don't know if I'll show the video. Depends on how much time we have left when I'm done talking here. They talk about stars releasing energy, and essentially this goes back to the Einstein equation. Actually, let me write it over here. And what is Einstein's equation? Everybody knows it. What is it? It's the most famous equation in the world. Yes, that's it. E equals mc squared. What's the E stand for? Energy. What's the M stand for? Mass. And c is actually the speed of light. The speed of light squared. So what this means actually is there's a relationship between energy and mass. Before Einstein, and we still kind of use this because it's a general like Newtonian term. We say that matter cannot be created nor destroyed, right? You can't create or destroy matter. That's not actually true.
Like you throw it in the sun, you can just get it.
Yeah, and stars actually destroy matter and create energy from that. It's not a lot of matter being destroyed, it just doesn't go nowhere. But as they combine molecules, there is matter that is lost and it's turned into the form of pure energy, and that is what is released from the sun. And so that is kind of where we get all of this energy that the sun is putting off. In this nuclear fusion reaction, there is a little bit of matter lost each time you do these combinations, which is the same reason that we get so much energy from nuclear weapons. There is matter that is converted to energy in those weapons, and that vast amount of energy is released. And so we kind of learned that from stars and from Einstein. So we already talked about how your stars form bigger and bigger elements. You'll note that on the periodic table, there are elements that are much, much heavier than iron. So iron is the biggest that we can form inside the core of a star. But you want to get bigger than that, your star has to explode. It has to go supernova. And so all the other elements past iron come from star explosions from really big stars. Towards the end of their life cycle, they form supernovas and giant clouds. And that's where you get your bigger elements created, which is why for the most part, not all of them, but many of the elements past iron, obviously not all of them, but many of them past iron are radioactive because they come from a very volatile place. They're formed in a destructive manner, and they're not really stable in the way that all the elements below iron are. I don't know that there are any radioactive elements below iron. I guess potassium is.
How far away can you be from
but not a lot of them.
supernova to feel its blast?
We actually are still trying to figure that out. To feel its blast, you'd probably have to be pretty close. But to get light or energy from it, you could be really far away.
Just like see it.
And they're actually starting to wonder if supernovas have somehow been responsible for extinction events on Earth. Not the dinosaurs, but there's lots of extinction events outside of when the dinosaurs got extinct. And they're wondering, did a really close star go supernova? Did we get a lot of energy from that? And the life here on Earth just couldn't handle it very well. And so we had a lot of extinctions. There are guesses that a supernova happened pretty close to here, and that the sky would have been basically like daylight for several months as that supernova took place and the light passed by us. That star going supernova, even though it was so far away, was just as bright as our sun, which is right next to us.
A few months.
Yeah, because it happens it's not like an instantaneous thing.
So it would just be light for a few months.
It wouldn't get dark. Yeah. Now that's just a theory, but when they put that stuff out there, they're pretty confident that it's at least a possibility if it hasn't actually happened.
Would that blast go forever, or would it eventually die out?
No, it eventually dies out. I don't know that we may have observed like a supernova or two, but usually what we see is the leftovers of the supernova. We see some energy left over, a gas cloud, and we kind of deduce that there was a supernova there. But I don't think we've seen an actual, hey, there's a star there. The next day, oh, there's a big eruption. And then a couple months later, now there's nothing there at all. If we have observed it, it hasn't been too many times. Okay, so I think we're done with that page. The next page is just going to talk about galaxies. How much time do we have left? Fourth period, 11:33. We got about 15 minutes. So this should not take too long. Hopefully it goes to the next page. Okay, next page is going to talk about galaxies. Know that they talk about island universes, not today, but in the assignment that we'll do later this week. They'll mention island universes. And basically the thing is, we're not in the center, we're towards the outside, but we're within the Milky Way galaxy. It's hard for us to see things that are super outside of it. We need really good telescopes, And for a long time, we knew about the Milky Way, we knew about all the stars around us, but we couldn't really see other galaxies in the way that we see them now. And so we thought of ourselves as like an island galaxy or an island universe. And the idea was, if you're on an island out in the middle of the ocean, I don't need to draw this. You all know what an island out in the middle of the ocean is. You're on this piece of land, and you can't really see any other pieces of land. It's just water everywhere as far as you can see. And that's how we felt early on looking out into space, that we were in our galaxy, and there's really no other galaxies within view from us. And we're kind of on our own in this own little galaxy island in a way. Once we started to design better and better telescopes and look at different parts of the electromagnetic spectrum, we figured out that not only did our galaxy have billions of stars in it, but some of the things we thought were stars out in space were actually galaxies themselves. And so, you know how sometimes, I don't know what's a good example of this. You know how sometimes on your phone you just have like, you take a picture and there's just like a little blur or something, but then you can zoom in and you actually see what's going on there. That's what those telescopes were. We saw just a dot of light and we thought it was a star. And then we got better and better telescopes and we were able to zoom in. Turns out it wasn't just a star. It's another galaxy far, far away. And we couldn't really see the details of it until we got a much better camera or a much better telescope. And so that's kind of how we understood, or we got to the point where we understood more about galaxies. They do go over the different types of galaxies. So there's actually 3 types. Spiral is going to be the Milky Way galaxy. That's what we're in. Elliptical is basically going to be a circular galaxy. There's no spiral arms. It's not spinning. It's just like a big sphere or an elongated sphere. It can be kind of a little bit egg-shaped, but it's called elliptical. And then the other one is irregular. It doesn't have any round shape. It doesn't have any spiral shape. It's just a weird, like, stretched out string. It could be almost anything if it doesn't fall into either one of these categories. A lot of galaxies are going to be these 2. These are going to be very rare. Let's see if they show some pictures down here. They have some pictures of some spiral ones. Here's just an elliptical galaxy. It just looks like a ball of stars. That's what the elliptical is going to look like. And I don't even know if they have any pictures of irregular galaxies. So, yeah, there you go. That's a little video segment. Let's see if they do. Because I had this. So this is the galaxies video. We weren't going to watch the whole thing.
The stars in a galaxy.
Sorry, that's very loud. Sorry, people at home. Let's turn this down a little bit.
Galaxy are born in clouds of dust and gas called nebulas.
Yeah, we don't need the whole
These
history.
are with the most advanced telescope at the Hubble had made one of the greatest discoveries in the history of astronomy. The universe contains not just one, but a great number of galaxies.
So there's a spiral.
This is the
There's
world
probably
of
a
galaxies.
circular, maybe even
It
an
has 2
irregular
giant
galaxy.
spiral arms and contains about 160 million stars.
If this were the Milky Way, which it's not because we wouldn't have a picture of it unless it's just a computer-generated graphic, we would kind of be like out here on one of these arms.
We don't have a picture of the Milky Way?
No, we're in the Milky Way, and we haven't even seen anything really outside of our solar system. And so no, we haven't seen anything far enough to be able to look back and kind of take a selfie of our galaxy, huh?
How do we have that? Or is that just made?
This could be a different galaxy, or it could be a computer-generated graphic. And so we could like think about what it's going to look like, and we have an idea of the structure, but we've never actually gotten a full picture of the Milky Way because we haven't seen anything that far out. And if we did, it would literally, when it took the picture and sent it back to us, it'd probably take thousands and thousands of years for that picture to even get back to us because it'd be so far away. And so we may never actually get a full picture of the Milky Way.
Everybody's hotspot.
I don't know.
Kind of a speck.
I don't know that this video is going to be
Way.
working, so we're not going to watch it. But yeah, this would be like an elliptical galaxy, a nice circular, maybe stretched out a little bit, but mostly just not a lot of structure to it. And then a regular would be quite a bit weirder looking and less common. And I think that's about it. They talk about the 3 types of galaxies. So that's really what they're going to ask you about on the questions today. They ask you about the types of galaxies. I think they ask about, or I ask about. It's not they, it's me. Ask about the nucleosynthesis and what element is the heaviest element that can be made in the core of a star.
What's the code?
And yes, the code, for those of y'all, I was going to say the code earlier so you didn't have to just go to the end of the video. Here's your code. It's on the board over here. So yeah, that's the code for the video today. That will be the last question. So you're going to answer that one too.
100.
What were you? Was your Chromebook open and you were answering questions
Well, I
while
did it last year. I just needed the code.
watching you? So yeah, if you have any questions, let me know. You should be able to answer all the questions. It's not meant to be hard. It's just meant to make sure that you were listening or you watched the video. So for those of you at home, if you have any questions, please let me know and I will get back to you and try to help you out. Thank you.